Hello everybody, and welcome back to another CIV 398 assignment tutorial. In this tutorial, we're going to be covering assignment 5, question 5, which is the last question of the assignment. So you guys are thinking, yay, almost done. But this question kind of sucks. So you guys are almost done, but not really, because this question, it's long. And you can tell by the amount of writing. I'm not going to read the writing because you guys already have it all in your assignment. You guys have read it. Because the gist of it is this. We have a beam that's hanging from the roof, and we're pulling down on this beam with that axial load P. Now, of course, there's going to be stress along this beam because we're pulling across it. And all this question really wants us to do is to determine the distribution of the stress component sigma 2 along the length of the beam. So you guys have already seen this in the lecture as well as in the quizzes. So you guys are already an expert of what this is asking. But the hard part about these questions is always trying to figure out how to solve it. Now, even though this question looks really long and it's broken down into many steps, to get from where we are now to the final answer, there's basically two things we need to do. The first is determine the differential equation governing the behavior of this beam. And that's usually the hard part for students, because the second part, solving the differential equation, is typically a little bit challenging and a lot of students would really not like solving it. However, we use Mathematica to solve it very quickly. However, if we have the wrong differential equation, well, it doesn't matter what we do in Mathematica, we're going to get the wrong answer because we need the differential equation to solve for the final answer in the end. So what we're going to do in this tutorial is I'm going to show you guys how exactly we get the differential equation, and then how do we take that differential equation and solve for it in Mathematica. So let's start talking about the differential equation. The key to finding these differential equations is drawing a nice free body diagram. So I have the picture of the beam on the right here, and what we're going to do is we're going to take an infinitesimal slice of this beam. So even though it looks like it's a pretty big slice of this beam, we got to pretend that this is an infinitesimal slice. And you're saying, Clayton, what exactly do you mean by that? I mean the width of this slice is dx2. And I'll probably just say dx because all the x variables in this question are x2 because we're only talking about the vertical direction. So I'm going to say that the width of this is simply dx. Now we got to ask ourselves, okay, what kind of forces or stresses are on this cross section? Well, the most obvious one is, of course, we have the distribution of stress, sigma 2. If we look at the one side of the beam or the top side of the beam, we simply have sigma 2 going upwards. And on the bottom of the beam, we have sigma 2 plus the change in sigma 2 with respect to x multiplied by that thickness dx. And what does this mean, this change in sigma dx times by dx? Well, that's basically the slope of the slope of sigma 2, and then we multiply it by the distance dx. So it basically gives us that change in x from each slice of the beam, each width of the beam. Now, unlike the nice quiz question, we have other forces we need to consider. And the first one is rho g. So rho is the density, and of course g is the acceleration. And if we think about the units of this, this is basically going to be the self-weight of the beam itself. And that makes sense. Let's say I had a slinky, I'm holding it from the rooftop. Well, I don't have to apply any load. That slinky will fall down because of its own self-weight. And that's what we're accounting for here with this rho g. And then, of course, the other one is a distributed load Q. So to make matters worse is not only do we have to consider the stress distribution, we have to consider the self-weight, and we have a distributed load Q around the beam. So the key that we're going to end up doing is we're going to take the summation of the forces is equal to 0. Static equilibrium. Nice and simple, Eng 130. You guys love it, I know. But the key to that is we're taking the sum of the forces. We're not taking the sum of the stresses or anything like that. We need a force. And right now, if we look at these are all over the place. The distributed load has units of newtons per meter. The stress has units of pascals or MPa, something like that. None of them are just in newtons. So what we're going to have to do is we're going to have to also find relationships between the area. So what I'm going to do is I'm going to say at the top of the slice, the area is simply equal to A. And at the bottom of the slice, the area is going to be A plus the change in area with respect to x multiplied by that thickness dx. And this right here is our complete free body diagram. And from here, we can derive our differential equation. So let's go into that. So if we have this free body diagram, remember I said the key here is we're going to take the sum of the forces along the E3 direction. So a little bit of a note here from the picture itself, you guys will see that the positive E3 axis is pointing downwards. So all those downwards forces, if you will be positive. Meanwhile, the upwards forces sigma 2 will be negative. So if we expand this out and find the sum of the force equal to 0, we're going to get this. And don't worry, I'm going to go through each of the terms. I know it looks pretty lengthy, but in essence, we just took all the summation of all the forces and made it equal to 0. So let's go down one by one. So the first component I have is that sigma 22 plus the change in sigma 22 with respect to x multiplied dx. So remember that this is a stress, but I don't want a stress, I want a force. So in order to go from stress to force, I have to multiply by the area. Well, we know that the area is going to be a plus the change in a with respect to x times dx. So there's my first component here, and once I multiply the stress and the area together, I get a force. The second one is that rho g. Now let's think about the units of rho g. Rho is a density, so it has kilograms per meters cubed, and g is an acceleration, so meters per second squared. I multiply them together, and I basically have that rho g is newtons per meter cubed, and I want it just in newtons. So what I'm going to have to do is I'm going to have to times by a volume. Well, we're going to have to do the volume of this slice. How do we find the volume? Well, it's simply going to be the area of the cross section, so A, multiplied by the height of the cross section, in this case dx. So that's why I have rho g down here multiplied by A dx2. That's basically taking newtons per meter cubed and then I'm multiplying it by the volume of that slice. Moving on, we have Q. Now Q is a little bit simpler because we know distributed loads have the units of newtons per meter. So I don't need to multiply it by any sort of area, I just need one length constant. Of course, it's going to be the width of the slice. So I'm taking Q and I'm multiplying it simply by dx. And then we look at the other side and we have the sigma 22. Well, we know that to go from stress to force, we just multiply by the area. Well, the area in this case is simply just A, and we have our differential equation in its ugliest form. But we're going to have to do some modifications before we actually start solving. So let's go to the next slide and say, okay, this is what we have in our current state. But let's see if we can make this look a little bit nicer. So I expanded it out. And what do I mean by expanded? I took those first two terms, the sigma 22 plus the change in sigma 2 with respect to x dx, blah, 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 and I just expanded it out. And the first thing that we're going to see is on the very left-hand side, we have a sigma 22 multiplied by a, and on the very right-hand side, we have a minus sigma 22 multiplied by a. Well, naturally, those are just going to cancel with each other. However, they're the only things that cancel. So we're going to have to be a little bit more creative in figuring out what exactly are we going to do to make this look nice. Well, one thing I noticed is that there is a dx term in every single one of these terms. So I'm going to factor it out, and then if I factor it out and the whole thing is equal to 0, well, I can divide both things by 0. So if I divide the left-hand side, I get rid of the dx. 0 divided by dx, well, that's still going to be 0. So effectively, I cancel out this. So now I'm left with 5 terms. However, there's one more simplification we can do. In one of the terms here, in the middle term where we have the d sigma times dA multiplied by dx2, we have to keep in mind that when we're actually solving this, we're taking the limit as dx approaches 0. And that's how we're solving for all these things. So in the end, this dx is going to approach 0, and because dx is approaching 0, this whole term right here goes to 0, because effectively dx is going to be 0. If it wasn't equal to 0, well, then we're getting into approximation methods. And we're not dealing with that. We're dealing with an exact solution in this case. That's why dx goes to 0. And in the end, this is what we're left with. And I'm going to put a nice big box around it because this right here is actually our differential equation. So I'm hoping that you guys go through the example, try it yourself, and try to get to this point here, because this differential equation, this is what you want to end up with. This is basically the solution to half your guys' assignment right here. However, it's very important to know where it comes from, because if you guys are given a midterm question, it's going to require you guys to find this differential equation. But by now, I'm sure that you guys are experts and you guys are just laughing at me saying, Clayton, this is too easy. Let's move on, make this a little bit faster. So yeah, let's do that. So remember I said in this question, there's basically 2 steps. One is finding the differential equation, which we just did. And the second one is solving this differential equation. So let's go take a look at that. So again, we have our nice differential equation, and let's look at what it's composed of. Well, we know that there's a bunch of constants, such as rho, g, and q, and we know all those. So that's no big deal at all. We know that there's the area involved, but we already know the area is a function of x2. I didn't give it to you guys specifically, but based on what you guys are given in the question, you guys can easily find what the area function is as a function of x2. And since you guys have the area as a function of x2, you guys can take the derivative of a with respect to x2 to give us the change in a with respect to x2. So if we're taking a really good look at this equation, The only unknown is sigma 2, 2. And of course, once we have sigma 2, 2, we can take the derivative to find d sigma 2, 2 with respect to x2, stuff like this. But the main question is it's not as simple as just solving for sigma. We have a function sigma 2, 2, but also a derivative of that function, the d sigma 2, 2 dx2. So the question becomes, how do we solve this differential equation? Well, by this point in your guys' careers, you guys have already taken math. I believe it's 209 or 201, whatever it is, the differential equations. And you guys are saying, well, I can solve it, but it's a pain in the ass. I don't want to do that. Well, good news for you guys. Mathematica can solve differential equations with ease. So this is why I said that originally this is a hard question, but the only hard part is really finding the differential equation, because once we have it, we're just going to throw it in Mathematica, and Mathematica will take care of the rest. Well, how do we do that? Well, Mathematica has a function called dsolve. So capital D, capital S, solve function. And this function, as you guys will see, will take in 3 arguments. But before we get into those arguments, we got to figure out, okay, what are the steps to do? So there's a bunch of different ways you guys can solve for this, just like everything else in Mathematica, but this is what I like to do. The first step is I just define the differential equation. So this is our differential equation from before, and what I want to do is I want to define it in Mathematica terms. So I'm going to say that dE, which is differential equation, you guys can call it whatever you want. If you guys want to say y is equal to this, it doesn't matter. Personally, I go dE is equal to this. So the first component, I got a multiplied by s prime of x. So s prime, well, you guys know that means the derivative of x, s prime of x. That's the first component. And then plus s of x multiplied by dA with respect to x. So that dA with respect to x, that's my derivative of a with respect to x above. And finally, rho g times a and then q. So all I did here was define my differential equation. I didn't say what it's equal to or anything like that. I just defined what the equation is. And once you guys have that, it's very easy because now we just go right into the dsolve function. So I put sigma, which is my stress. It's going to be equal to dsolve and then 3 components. The first component is going to be my differential equation and what it's equal to. So I say that dE, which is my differential equation, is equal to 0, because if we look above, we know it's equal to 0. So that's kind of trivial. The second one is, what function are we trying to solve for? Well, we want to figure out what the heck s of x is. And finally, what is the variable inside of that function, which is just simply x. So even though the differential equation is very complicated, the Mathematica procedure seems really easy. And I put a little note here, it seems a little too easy. And I put a smiley face, I'm kind of getting you guys excited. But aren't you guys a little suspicious? Well, you should be. Because if you guys enter the dsolve function just like this, you're not going to get the final answer. Because now we're going to have to think back to those actual math courses and remember, oh, wait a second. The thing that really sucked ass about differential equations wasn't solving it, it was finding the coefficients. So what happens when you guys solve these functions, if you guys were to just solve it the way I showed you before, Mathematica will give you an answer, but inside of that answer, you will get something called C1. And that basically means a coefficient. How do you solve for that coefficient? Well, that's what we need to discuss right now. So the main question, how do we solve for these coefficients? In this case, we should only have one coefficient, C1. And you guys may remember, we do that through boundary conditions. So what I can do is I can say, at this part of the beam right here, the stress is going to be this. And from there, it can actually modify the equation, do some algebra, and it can solve for that coefficient. It's not a tedious process, but I don't know. I'm lazy. I would rather use Mathematica than do it myself. So in our case, we know that x is equal to L, or at the very base of that beam, at the very bottom, we know that the stress there is going to be equal to that force P divided by the area at the end of the beam. So what I'm going to do is I'm going to figure out what that stress is, and I'm going to call it S-end. So send, if you will. Then what I can do is I can go back to my dsolve function and incorporate this boundary condition in there. So after I do that, my dsolve function will be this. And you guys saying, Clayton, what happened? It looks a little confusing. Well, I took this boundary condition here, and then look where the dsolve function is. The dsolve function still has 3 components. The first one's the differential equation. The second one is s of x, and then the final one is just x. But inside of that first component, I put the squiggle brackets, and I put in 2 arguments. So my first argument is the differential equation dE is equal to 0. So this is from before, that's nothing new. But then I put a comma, and I put in my second argument. And this is the boundary condition right here, where I put S of L, so the stress at the x is equal to L is equal to S end, or send, if you will. And if I do that now, Mathematica knows to say, okay, I'm solving this differential equation. This boundary condition must hold true in the differential equation, and then it's able to solve for that unknown constant. So once you guys throw this into Mathematica, you guys will get the final answer, which is the kind of the end answer to this question. So it was a long, tedious process, kind of boring, I know, but I hope you guys learned something. That concludes assignment number 5. You guys should be nice and happy. 5 assignments done, only 5 to go. The course is flying by. You guys are doing great. So thank you guys all so much for listening. I really appreciate it, and I will see you guys in assignment number 6.